Untitled Machine Learning and Artificial Intelligence. Dr. Chris Beaulieu is tonight's Howard Steinbach Memorial Lecture, and we're looking very much forward to this talk.
Good. Well, thank you so much, Thomas, for that lovely introduction. The one picture of the family working on the cottage was the only actual time they did any work. That's okay. It's really an honor to be here and to be invited to give this talk. I'm going to go back one slide here. I didn't get to meet Howard Steinbach, but I'm going to speak tonight about a couple of contemporaries that he had when I get a little bit further into the talk. I want to thank Lynn in particular for making this possible, and Chris and the department for having me up today. And thank you again, Thomas, for the nice introduction. When I was asked to give this talk, I didn't give this title. I actually proposed this title, which is very similar, right? Computer diagnosis of primary bone tumors. And the interesting thing about this title is that it came up after reading this article. Okay, computer diagnosis of primary bone tumors, and our authors are Lodwick and co-authors. And the interesting thing is this is from 1963. So this is when Margulis took over the department. John F. Kennedy died that year. Outer Limits was on TV. It's just a long time ago. I was around, but not that old at the time. So this field is not new. And so one of the messages I have tonight is that, we talk a lot about AI and things like that, but this has been around for a long time, and we need some perspective on it. I do have a little grant from Phillips. I'm going to just touch a little bit on MSK imaging to frame things up. I'm going to spend a fair amount of time on AI and machine learning, probably half the talk, because I think a lot of us don't know a lot about it, and if I can provide some perspective for those that don't, it's going to be important. For our trainees, for example, this is, I think it's analogous to a new modality. It's like CT or PET-MR or something like that. People are going to be talking about this for years, and we need to understand it. And then I'll focus in on AI and MSK and some of the work we're doing and other people are doing. So my objectives are to explain some of the principles and to review some of the current applications, and as I go along to highlight some of the pros and cons. I like baseball, and so I have a baseball analogy here. And so the analogy or metaphor, or whatever the right term would be, is how do we get from where we are or where we would start out to home? And home, in my mind, would be where AI actually improves patient outcomes. Okay? So when you look at the very beginning of radiology, you can have Röntgen there in 1895, and then we'll go around the bases, and you may be able to predict that we're not quite reaching home base yet, but we'll kind of march through that. So for those that are not MSK imagers, I just sort of splatted up a bunch of MSK images, and these are things that we do every day. It's a lot of high-tech things, and some perhaps thinking about it as low-tech, radiographs, MRIs, CT scans, 3D, and so on. A beautiful thing about MSK is that the radiographs are still relevant. A lot of specialties have kind of passed them by, and you use cross-sectional imaging as much more of what they do. But especially for bone tumors, the radiographs are still very relevant, and in fact, they're probably the most important step that's taken in analyzing a patient with a bone tumor. So in this patient, there's a lesion here in the femoral neck, and we can look at that and say it's well-defined, so we think of that as a benign-looking lesion. Here's an intermediate-looking lesion in the ulna here in a patient. It doesn't have that white border around it, so we know it's not quite as benign as this one. Maybe it's an aggressive lesion. It could even be malignant, but it's probably sort of intermediate. And then something like this in the humerus, where this is a very irregular lesion, and probably everybody in the audience can look at this and say, well, that one looks well-defined to me. That one does not look as well-defined. So that's malignant. Okay, so this is where I'm going to focus in, as we go along on the bone tumors. It's a very difficult area of MSK radiology, and as I said, the radiographs remain one of the most important features. And so even early on in diagnostic radiology, people started to analyze features of röntgenograms, what they were called at the time, of benign bone tumors on this table, and they're listing a number of different lesions here, and then the different imaging features. Where were they located? What did they look like, and so on. So this was kind of the information, the knowledge that was starting to be built up about if you were in the reading room reading these scans, what are you looking at and how do you make the diagnoses? That's from 1924. And so if we look at the baseball field at this point, I think we've moved from the beginnings to the work of Lodwick, which I'll talk more about in a few minutes, the first base for sure, and then we still have a long ways to go. So let's talk about AI and machine learning. And a number of these slides I modified from our Amy group at Stanford, so I want to give them credit. If you go to these AI talks, people show basically the same slides. Mine are going to be better, but a few of them are the same slides. So this is the sort of Venn diagram, if you will, where artificial intelligence is the broadest way of looking at things, and it's basically when computers do things that mimic human intelligence. Okay, machine learning is a subset of that, and this is where we're going to talk about this and go through it. But it's where models are built based on the computers using different techniques. Within machine learning is a subset of that called neural networks, and then the current hot topic in the world is deep learning, and that's sort of a subset of neural networks, right? Mark Coley wrote a nice article, a review article, on how to implement this in the department, and I would recommend that to all of you. And in machine learning, he gives this definition, which I think is quite good. It's a broad class of statistical analysis algorithms that iteratively improve and learn in response to training data to build models and algorithms for autonomous prediction. Okay, it's a little bit of a mouthful, but basically the idea is these are statistical algorithms that learn, that allow you to put in unknowns and use that learning and that trained data to predict an outcome. A couple other definitions are worth hitting on. So-called supervised learning is what we see a lot of, and that's where the user supervises the training by providing known answers, like radiographs say labeled with fracture or no fracture or pneumothorax or not. And that's mostly what we're seeing these days. There's also unsupervised learning where you can basically throw a huge number of images, for example, at a computer and just say, computer, figure out what this is all about, and perhaps classify it into different groups. There's hybrids of these things as well, but much of what we'll talk about tonight is supervised learning. I also want to draw a distinction between CAD, traditional computer-aided detection, and machine learning. And so CAD is basically where somebody wants to look at a feature in an image, and you create a mathematical algorithm to go and look for that specific feature. And I'll give an example of that. It's very highly tuned, it takes a lot of mathematical knowledge, and so on. It's very directed. Machine learning is a broader area of research that capitalizes on often multiple features in the image. It's much more generically applicable to things. And this is why there's so much going on now in machine learning and deep learning, because it's very broadly applicable. I don't have time to tell the whole body imaging versus MSK story. The bottom line is there were no jobs, and somebody said, would you mind doing some bone? And I'm like, I will do some bone. And then it went from there. That's the short version. So I was a body imager, and CT colonography was coming around. So I worked on this a lot. And so this is the example of like highly supervised learning, CAD, computer-aided detection. This is not deep learning. And so what we were doing is developing tools to find polyps in the colon. Here's a 2D image, and here's a 3D image, okay? And that field was evolving in the early 90s and late 90s, and so we had graduate students that crafted these algorithms. This one looked at the colon surface and projected normals to the surface. And it turns out if you look at a polyp, those normals will converge in 3D, kind of like this little yarmulke diagram here. And versus a fold, they won't converge as much. So that's sort of a sensor for these polypoid structures. A different mathematical formulation of the colon that we did in conjunction with Lon Summers at NIH. Another grad student did this one, looking at colon surface shapes and finding polyps here and so on. These are very intensive things. And the algorithm, the equation that described David Peck's thing is this horrible equation that could make your head explode if you actually tried to understand it. But that's a whole PhD thesis. So two of these things are a whole PhD thesis just for these CAD algorithms. Okay, and it turns out they work okay, pretty well, 85% or whatever, but it's only good for that one thing. So it's not very applicable broadly. Another thing that I just mentioned that we worked on is so-called content-based image retrieval. And this was a project where I was still in the body imaging world, if you will, looking at liver lesions. You know, the body imaging stuff is good because people are not dying of meniscal tears. So it's hard to get funding for some MSK projects, whereas in the world of body imaging, it's much more possible to get funding, although this one actually failed to get funding. But anyway, that's a side story. So in this project, we took liver lesions on CT and we characterized them by different features that were semantic features, labels based on perceived features like shape, margin, and so on. And we crafted a machine learning system that could then rank unknown lesions like this hemangioma here and put lesions that were similar to it closer and lesions that were not similar to it further away. Content-based image retrieval is what that's called. That's still a relevant topic. Okay, so now I want to do a little tutorial, if you will, because what is machine learning? Can I just ask people, if I ask everybody in the room, how many people could explain what machine learning is? What's the essence of it? Several of the folks, but I'm glad not everybody raised their hand because I'd have to shorten the talk. So the task I want to go through real quickly is let's build a machine that distinguishes apples from bananas. Okay, it's kind of a real life, possible thing. It should be a fairly easy task. So the question we have, and it's important to know what question you're asking is this fruit an apple or a banana? And so we're going to take some training data. And so let's say we have 100 pieces of fruit total. We have 50 apples, 50 bananas, and they have different features, right? Things that we can see just by looking at them or by measuring things in the lab, color. We could weigh the fruit, we could measure the diameter, we could measure the sugar content, and so on. And so we take these training data and we find these features for those, and then we create a table. So here's a feature table, right? So you have the apples, the bananas, the color, it tends to be red for apples, yellow for bananas, weights, and so on, right? So this kind of makes sense. Bigger diameter for apples than bananas. So the task is we want to build a machine that can distinguish between these two things, right? Okay, so let's just say we only had color. Color red, color yellow. That's actually pretty good, right? It's almost perfect in this situation to determine these apples from the bananas, but life is not quite that simple, right? But if you were that lucky, you could draw a regression line separating those out mathematically and say all apples, all bananas. The not simple part of the world is this, where then you have, well, this apple ain't quite red, is it? What if this yellow apple? What about this banana that's starting to go bad? Then, if you try to distinguish those with a linear regression line, you draw a line like this. That doesn't really work because you're missing this one. That one doesn't really work either. That one doesn't work either. So it's a more complicated thing to do than to separate those out. You could say, well, I'm going to craft this crazy, highly mathematical algorithm that separates these out like this and goes around that golden delicious there. But this is what's called overfitting. And so this mathematical formulation is probably not going to work for the next set of apples and bananas you do because it's so highly tuned for this particular batch. What if you go to two features? So let's take color and add the weight feature. So here the weight now is on the y-axis. And that does a better job, perhaps. This apple is over here now, and this one's still up here. You could do some sort of separation regression like that. And separate the classes, you're missing this one. So maybe you need a third feature, color and weight, and then diameter. And diameter is an important feature, right? Because the bananas are narrower than the apples. Now that golden delicious or whatever that yellow one would be comes over here, and you can separate out the classes based on a linear plane between them, a linear line or a plane. And in machine learning, these kinds of things are called hyperplanes, right? Hyperplane or a plane or hyperplane between classes. So here's 3 features. You could go up to n features, right? And you're basically building this model so that you can separate out the features of interest. So this gets back then to the early part of AI machine learning, which is this thing called the perceptron. And this is sort of a way of thinking about a little bit about the way our brains work, but that's more a neural network. So in this situation, you take input features, let's say that's color, diameter, weight, and then you put it into a machine that puts a weight on each of those features, an importance on each of those features, and then it calculates a sum, and then it comes up with a decision. Is that an apple or a banana? Okay, so let's go through that just a little bit more here with this little machine that I put together. So let's say the truth is that we have half bananas and half apples, 50% in each, okay? We have a start to the algorithm. Here's the question, apple or banana, and then this is the decision point. And so you have color, weight, and diameter. And the little omegas here, those are the weights. That's how much emphasis we're going to put on each of these features for the first run. So you multiply by that, and you get some percentage coming out of apples, some percentage coming out of bananas. And basically, you run that test over and over and over for all of your samples, and you end up with some result. So what the machine does at first is often it just uses guess. Or you say, let's just start by setting all the weights to be equal, 0.33, add up to 1 total, and see what happens. And so in that situation, the apples and bananas 37 to 63, so it's not doing that great, right? So this machine's not that smart. So what if we help the machine learn? And this is really, if there's an essence to this concept, this is it. So what we're going to do now is we're going to change the weights. And we're going to change the weights either randomly or systematically. And we're going to say, well, color, let's weight that here, weight the actual weight here, and so on. We're going to recalculate the results, and then we're going to compute what's the difference between this result and truth. I'm going to keep going on that, keep changing these weights until we get to, after some nth iteration, of something that's like, you know, a pretty good result, 48 to 52. That's pretty close to the 50-50. And so ultimately, after all this computation, the machine has learned these weights to optimize the outcome. So then you have this trained algorithm. You can put in a new fruit weighted by these parameters, and hopefully that's going to give you a much better answer than if you gave just the equal weights. Now you'll see diagrams like this. So what this is getting back to radiology here. So breast lesions, benign versus malignant, separating out by spiculation versus calcifications, might distribute in a kind of random or semi-random kind of a way. The machine learning algorithms, you'll see all this jargon and all these different terms like support vector machines, radial support, random forest. These are all algorithms that attempt to separate the data and learn the data to get the best outcome. Okay, you see the different patterns. So the red is malignant, the blue is benign, different mathematical formulations for these algorithms. Neural networks have been around for a long time, and that's another way of basically adjusting all these weights to try to come up with a better outcome. And so here's breast masses. You have an input layer here, and you have a hidden layer. And this was one of the kind of problems with neural networks is it's sort of this black box. You don't really know what's going on. But the essence is you run all your data through one of these neural networks, you get an output layer, and you try to optimize the results for malignant versus benign. Okay, so that's been around for a long time. And there's papers on that from the 80s. There's a nice paper from John Boone at Davis in, I forget, like 1990 or something like that. But AI research is kind of puttered along. This is the timeline of AI research, and I won't go into great detail, but say 1950, things are starting with this so-called Turing test. We're going to be up here. We'll talk about that in a minute. Ups and downs. So here's strong funding and optimism. People think it's really going great, and so on. And then people realize, you know, these machines are pretty brittle. The neural networks take a lot of time, and they're not that accurate, and they're only so good for so much. So there's like this winter, AI winter. Then things get better again. Then there's a second AI winter. You know, kind of disappointment and disillusionment with this technology. And then the internet bubble here, that's like early 2000s. Things are getting better again. And things got really, really, really a lot better in about 2012. And they got better because of this. ImageNet is one of a few databases, but ImageNet is something that was created by Fei-Fei Li at Stanford, and it's 14 million images of kind of natural scenes and sort of real life, like spiders, flowers, apples, stuff like that. They're all labeled, so they have labels with them, different types of birds. You see all the different, and so the challenge that had been put out was like, what can your computer figure out what these images are? Can you train a system to separate birds from spiders and so on? And so back in about 2011, if you'd run those images through your computer or a system, it would get about 75% right. You'd miss 25%, mislabeled. In 2012, somebody created a new system that actually almost halved that. And that was work at University of Toronto where they first did these deep learning algorithms. So we'll talk a little bit more about it in a second. So a huge increment in 2012, all the buzz. And then since then, other groups, NYU and Google and even Microsoft has done better and better on those challenges to get even better performance than humans can get. Like humans can only miss 5% of the images. So this was when a big breakthrough occurred. And this is based on a couple of different things. One of the big things is these GPUs, graphic processor units. And these are the things that if you have a gaming computer at home, these are these really powerful parallel processing machines that allowed you to compute for hours and hours and hours. It still take a long time, but it's really a huge increment. I don't know what the factor is, let's say 1,000-fold in computational efficiency compared to your CPU, which is basically your desktop computer. So that was one thing. And the other part is just recognition that these deeper algorithms were actually valuable, more valuable than they previously thought. So then instead of the single layer neural network, people started coming up with these multi-layer networks, the so-called deep learning and convolutional neural networks. And so here's the images going in, then there's all these different layers here, input layer, multiple hidden layers, and then an output layer that if you have a powerful enough computer, you can compute the weights between these billions and billions of different nodes and come up with a pretty darn good answer for that output layer. A way to think about this, just from a kind of intuitive point of view, is that much of what these things are probably doing is looking for image features. So the first layers might start to look for edges. The second layer might start to look for combinations of edges and so on. And I have another slide coming up here in a second that shows that better. So this architecture of these neural nets, the one I showed with the single layer, just one in here, but then look at all these different layers within the neural network, millions of parameters, hundreds of thousands of these nodes or neurons in there, and really, really, really powerful computing. I won't talk about transfer learning at the moment. So the other thing that's happened is now the companies have made these software libraries free to download. So you could go home later tonight, you can download some of the Google Inception architecture software, TensorFlow, and you could start doing machine learning later tonight if you want to do an home AI project, right? You can't build a cottage with it, but you could do something. So you don't actually have to need to know how to code. It is kind of a black box, right? We won't talk about that too much. But so people are doing really useful things now, like, can you distinguish blueberry muffins from chihuahuas? And I put this up because it's cute, but it's also like, we're good, like humans are really good at this sort of thing. So you can all look up there and you can tell which are muffins versus chihuahuas, I hope. Little kids can do this too. Computers are not quite always perfect at this task yet. So there's a ways to go. But people are probably like, well, if I can do the chihuahua, maybe I can do, pneumothorax. And so all this stuff it's available to us at large, right? We're living in this AI world. There's like, word completion here. So if you start typing in radiologist R, it comes up with suggested terms here. A little bit. Suggesting movies. We hear that these devices now are actually recording everything we say at home and putting that into a model of what your life is like, right? I don't have these things, but be careful. Pinterest. Spotify is a good example. I like this because I finally got Spotify. I'm coming into age, and so I'm like, how does that really work? And my music is morphing from sort of like, let's say, classic rock and roll to sort of like towards country western. I'm like, what's happening here? Well, if you look into it, these algorithms, the machine learning algorithm, they're doing things like looking at, okay, what genre was that song that I listened to? How long did I listen to a song? And did I say I liked it or not on the device? I don't do this part, but it could be getting recommendations from friends or family, or if I had Facebook, it's like other people like that song. And ultimately what it's doing is it's basically creating these new playlists of songs that I like more than others. So it's pretty cool, right? And it kind of works. And so it might be like, Thomas, I don't know if you use this, but it might be like, we're recommending this new song by, Nickelback or something for you, or Vic Damone. I don't know what your taste would be, but anyway, so machine learning in action. For me, I think it's looking at the words in some of the songs, and if they're country western songs, they tend to have words like whiskey and truck and stuff like that. I don't really know, but I'm trying to just get the concept across here. Okay, let's get back to radiology. So I hope that's a little bit of a tour of machine learning and AI. So people started applying this to radiology, and the data sets are big. You need really big data sets, ideally, to train these deep neural nets. And so this was a paper that looked at 112,000 chest radiographs on 30,000 patients and basically says, here's the input, we run it through our algorithm. That may take days or weeks to train, but once it's trained, it's really fast to decide on a new image, and says, well, there's a hot spot down here that looks like pneumonia. And what you'll see in the literature is all these ROC curves. And we're hopefully pretty used to ROC curves in radiology from a long time, but they're being used more now. And so this paper talked about all these different classes of diseases, and the ROC curves are all really good, right? And so it's like we can diagnose certain pathologies at a level comparable to practicing radiologists. So that's terrific, right? Just look at pneumothorax there for a second. That's the example I'll use in a minute. Really high accuracy for detecting pneumothorax. So Andrew Ng, who's a terrific individual, great computer scientist, said, should we be worried about our jobs? Well, breaking news, folks, we can now diagnose pneumonia better than radiologists. So, it's pretty bombastic, right? And the popular thing to do seems to be to compare all this stuff with what radiologists can do, right? And so maybe that's useful, it makes sense, but it's also maybe not the right question to be asking. It's not isolated to radiology. So here's dermatology. It can actually determine benign versus malignant skin lesions and do better as well as dermatologists. It's good. Sometimes you have to be careful because in one instance, it turned out if you're a dermatologist and you see something that you think is malignant, you're going to put a ruler on it and take a picture with the ruler on. Where it's benign, you probably don't measure it. And so there's a paper, I think, that says, well, it's actually detecting the ones with the rulers and saying that it's malignant, right? This is not that particular one. This just came out and says, doggone it, now AI is as good as pathologists for lung cancer. So, it's got potential, but it's not perfect. Let's go into the MSK stuff then. So this is the requisite witty quote that I had to put in my talk here for this type of an audience. If I've seen further than others, it's by standing on the shoulders of giants. And so, okay, giant number one, these two folks were kind of contemporaries of your dad, right? 1918. Lodwick, I didn't know, he was 1917 to 2012. He's the one that wrote that first paper in 63. He was a computer guy back when the computers looked like this. There's probably a huge, house behind it, but that's early computer. Wrote a book on it. Wrote a book on computer-aided diagnosis of bone tumors, right? Crazy. 1965, and he's got this monograph that if anybody wants a copy of it, went through and diagrammed the lesions, had images of lesions and classifications of different features, so periosteal reaction and margins and so on, and basically built this into a computer algorithm, probably Fortran cards or something, manual cards at the time. Basically, he said, we can apply these Bayesian network type models. This is not deep learning, it's not really that fancy, but we can say, just like we did with the apples and bananas, like, okay, these things have features, right? So their color, weight, and so on. There may be features that are intrinsic to the fruit, like in the blue, or you might even include something else that's extrinsic to the fruit, was it from Washington State, or was it from Ecuador, or whatever, right? So all these features could go in. And the Bayesian formula calculates the probability of a result based on the presence of a particular finding, okay? So in this one, you might say, given that the color is red, what's the probability that that fruit is an apple? And if you have enough data, you can have that work. So let's get back to radiology. So here's a bone tumor. You have size, margins, periosteal reaction. Then you have some demographic features here. And you can ask this question, given that that margin is sclerotic, it's white, what's the probability that this is a benign lesion or malignant or a certain type of tumor? So this is sort of the essence of Lodwick's work. And so he has this in his paper where he's got a table of features and an example here that I won't go completely through, but he's got the demographics, the location, and the type of lesion. And the humorous here, and his system would go through and predict the diagnosis. And the bottom line is that it's about 80% good. Right? So pretty darn good for 1963. This was a small data set, like 77 cases or something like that. So really limited data set. And he felt like he was actually himself around 80% accurate. So it's performing just about as well as this expert. Pretty cool. So that's the result there. We were talking about Henry Jones, but Henry Bones Jones was a colleague of mine at Stanford, and he actually coincidentally lived the exact same time frame as Ludwig, 17 to 2012. Somebody came up to me a couple weeks ago and said, "We had a typo in that slide." I'm like, "No, I don't." Just coincidence. And Henry was a collector. He collected, this isn't his collection, but it looked like this, 1,600 bone tumor cases when he, in his 59 years service. He copied all the films, right? This is before computers. And so when he retired and then passed away, he gave this collection to me. So what we did is we took all the hard copies and digitized it. I got a student that was crazy, but we paid him. And, we paid him to digitize these things. It took hours and days, but basically he did 22,000 images and 1,600 cases through this film scanner like we use for the film library. You know, and so it was worth seriously, like zooming in on it, zooming in more. They're actually beautiful images, and now we had all the pathology, we have the diagnoses for all of them, and even the medical records for these that Henry collected. So it's quite a collection. So what we did was we cataloged those cases, and here's the cases, the most common cases to the least common. You can see like lots of fairly uncommon cases like osteosarcoma, and then going down the list to things that are fairly rare. But we got up to about 800 cases that we thought were really the best examples of things. We're like, how can we use this? Can we rebuild this kind of a Bayesian network to predict tumor diagnosis based on this? And of course, the answer is yes. And so we actually built this software package called EPAD at Stanford. We originally called it iPad, but somebody stole that name. It's actually something, if you're interested in this tech, you can download it. It's free. You can install it. There's hundreds of users across the world now, and it's a useful tool because you basically build these templates that you can put in and say, I want to record age, gender, bone, or liver location, whatever you want, and then it allows you to create an ROI and then record that in a very structured way. So for these 800 cases, we recorded 18 different features. So we have this huge matrix of features for these 800 cases. So then when I say, well, does this actually work? And it's a little bit complicated, but again, I want to come down to this bottom line here. If you ask the question for the lesions that are fairly common, the more common diagnoses, there's about, this is only 10 distinct diagnoses, so a fairly narrow band. The differential accuracy is what we call, if it picked up the right diagnosis within the top 3 choices, we call that correct, and that was 80%. Okay, so not perfect, but probably pretty close to what experts would do, so we're encouraged by those results. I'll come back to that in a few minutes, but I want to point out that we're not the only ones that have worked on that, and there's other people that have done Bayesian networks, like Chuck Kahn and Mike Richardson's got an online thing based on Ludwig's work. There's been these types of work where they have their own kind of user interfaces, and one of the things that I want to sort of emphasize is, as radiologists, if we are building these systems and we have, maybe they're really accurate and producing results, we really want it to be user-friendly. We're not going to be putting in some ugly, no offense to the author's user interface, you have to click a bunch of boxes and put that in. It just has to be really user-friendly. So that's a challenge that we have to get over. I would say that the midterm work that's been done and our work, I'm not giving us complete credit for getting to third base, but we're definitely making progress in these problems. So we've done some other work, and so all that work is basically based on word labels, semantic labels of these things. No image processing, nothing like that. You could look at the images and do it. But we have the images. Those are scanned in images, so they have their limitations. But one of my postdocs, Iman Banerjee, built this relevance feedback system that basically takes and carves out the region of interest and does a bunch of mathematical computations on it, computer stuff. And it combines this feature space with the word space. Okay, and so now we have a combination of semantic and pixel space, and this actually improves the performance somewhat. It also, we built this into a user feedback system, so what you could do is it produced an initial set of similar looking cases, but then the user could like click on things and say, I don't like that one, I don't like that one. And as you give it feedback in that form of learning, it actually improves the outcome. So that's one little project. We're doing a lot more now too, and I don't have time to get into a lot of it. It's actually fairly early work, but we're building in the world data. So I'll show you that in a second. We're getting native DICOM images. So I have a big collection of bone tumors that I've collected over my career from our tumor boards, using more image processing and image-based features. I'm keen on image user interface things, and then there's all kinds of other things, and I'll touch on some of these that we could be doing beyond bone tumors. The cool thing about bone tumors is that they're particular about where they occur in the skeleton. So if you're doing work on lung or breast or liver, the lesion is either in the lung or it's in the breast or it's in the liver. So you don't really know where else it is in that organ. But in the skeleton, things have a predilection for different bones. So the Mayo Clinic, for example, has this book that they put out on 10,000 tumors, and it shows the statistical distribution of all those lesions throughout the skeleton. They also include gender, and they include age. So this is really useful predictive information, right? So there's that. There's also the Campanacci data set, registry, if you will, from Italy, where they have the same kind of thing, another about 10,000 cases. So the lesions are distributed within the skeleton in this way, but they're also distributed, whether they're centered in the bone or eccentric. And so we have one of our residents actually who's making all this information computable as well. So in addition to the Jones data set, the 811 cases, we're putting this into a huge spreadsheet as basically this evidence machine that we could use to like predict outcomes for unknown cases. Henry also collected literature, so he left behind all his folders, and I could probably dredge this up from the library these days, but he's got all these articles that are like 218 cases of giant cell tumors. So we're scraping the data out of those to make it computable. One little quick Henry story is I went into the reading room, many years ago. He's sitting in there. He's like in his early 80s. He's still working and cranking it out, right? And I said, "How you doing today, Henry?" He's like, "Oh, pretty good, pretty good." And he's like, "But you know what? If I was your age, I'd be calling 911. If I felt this way when I was your age, I'd be calling 911." He was hysterical. So that's one thing. So we now have about 60,000 tumors that we have in our probability tables. Quantitative analysis, right? So there's rich image data that we have. So here's a tumor. We can do a region of interest around it. And now we can extract some patches around the boundary to look at the boundary of different areas. And these types of input, whether around the boundary of the lesion or the internal part of the lesion, that can be fed into a neural network or a deep neural network to help predict diagnosis. Other tasks. So other folks' work I just want to touch on briefly, and then we'll kind of come to some wrap up here. Bone age has been something that has been a challenge and people have worked on as well. I'm not quite sure how huge of a burden it is in the reading room to do bone age, but it takes a little bit of time, and probably more than the burden of time, it's variable, inaccurate, and so it's good to have it be more better inter-observer variability or less variability for the patient outcomes. So in this model, the computer algorithm did better in terms of inter-observer variation than the human readers. So he also produced these heat maps. I call them heat maps. It's probably not quite the right term, but it basically shows when the algorithm runs a case, what's it looking at. And so here's like red spots looking at areas of carpal bones, and it looks like it's sort of relevant for this bone age topic, right? It's not like looking at irrelevant information. So the variation in that model was lower, than human readers. There's this upper extremity example that's been done at Stanford actually, and 40,000 cases so-called prospectively labeled. In this situation, the AI model, it didn't do quite as well as radiologists in all cases, but the summary of that was it got close to radiologist performance. And in this task, it wasn't like, oh, can you diagnose this particular specific mid-humerus fracture here? It was more of a triage thing, like, is this normal or abnormal? And people are now saying, oh, we'll use this as a triage mechanism. We're going to decide, we're going to reshuffle the work lists on PACS. We're going to put the abnormal stuff at the top and the normal stuff at the bottom. It's kind of a good idea. I'm not sure it's ready to go yet, but that's the concept. That's the kind of result that a lot of people come up with here. Other folks have worked on fractures, and so what you'll see here, there's nothing behind this label. They're promoting the idea that if you are operating in this point and then you use the AI model, you actually get better in performance with augmentation with the algorithm. Here's another example with 256,000 cases, very high area under the ROC curve, huge number of images, around 80% performance, but it depended on the type of the neural network. Different examples of fractures. So some things are really obvious, right? And I think one of the challenges is it's not really clear to us which fractures this is picking up and which it's not. I mean, some people will show, like this pediatric example, shows some of the false negatives, and that's helpful. And as you might expect, the false negatives are like really subtle, right? And that's what we miss as radiologists. The blue box here is pertinent because this is from England. They said, you know what? We're 200,000 cases behind this month on plain x-rays and 12,000 cases behind on cross-sectional. So we could use something like this if it could help prioritize. A little bit about limitations. So one thing you may not realize, and this is back to the pneumothorax thing, is that for the so-called the transfer learning that people tend to do, you need to downsample the images to match that ImageNet database. And so here's a native chest radiograph. This patient's got a big pneumothorax. Here's the pleural edge here. This is all extra pleural gasp. 2K by, roughly 2K by 2K image. It's downsampled then to 224 by 224 to compute. So are you going to lose information based on that? You sure are. So let's look at this as a scaphoid example. So let's say you have an algorithm, you want to detect scaphoid fractures, and maybe the native image resolution is this. Here's the fracture here, there's the fracture. But you know, in order to fit it into your algorithm, you have to downsample it to 224. You can barely, I don't even know if you can see this fracture at all, right? And so when you look at the results from these studies and you see it's so great, you have to really think, what are they really actually looking at there? Because I would really not want my system to miss this scaphoid fracture. Same thing is true for pneumothorax. So here's this pleural edge, and here's the downsampled one. We had a lab meeting a couple weeks ago, and one of the grad students looking at this, the whole ChecksNet database, was talking about pneumothorax. And he said, you know what? We're looking at that more. It's like 90% good, but it turns out it's like 95% good detecting if people have a chest tube in place. If they don't have a chest tube in place, what's the predictive value for pneumothorax? 3%. So it's not even looking for pneumothorax, it's looking for, and I'm probably embellishing a little bit there, but you have to be really careful. It's looking for like a confounding variable, like, you know, the cloudy sky or the ruler or the presence of the chest tube. So, you know, maybe we should put chest tubes in everybody and then you can detect it in the thorax. So because of that reduction in resolution, you have to be really careful. And I think, so as radiologists, we know about this resolution and subtleties of things, and the computer scientists, hopefully most folks are aware of that, but the lay public certainly doesn't know about how subtle things are, so we have to be really, really careful. Others are cropping images, so that's a better way of saving resolution. Here's one where intertrochanteric femur fractures can be detected as well as or better than orthopedic surgeons. Other applications in MSK, like spine applications of computer-aided detection from Ron Summers at NIH. Here you can detect sclerotic metastases in the bone and differentiate that from osteophytes. Look at fractures here. Here's spine MRI, looking at intervertebral disc, desiccation, neural foraminae. Boy, I would not mind having that work at all in the reading room, right? So that would be great. We're working a little bit on scoliosis, and then Sharmila said she's working on scoliosis as well. I'd be happy to give up all the scoliosis cases to the computer. And it might be good because it could be more accurate, and more consistent than the readings that we do. Work that's been done here by Valentina and others. This is a complicated slide, but a multi-layer neural network that looks at knee cartilage and menisci and things. And so for detecting things like meniscal lesions, very high ROC performance for that semi-easy task. And we were talking today, and it's like, if we can't make it work on the easy tasks, it's not going to work that well on the really difficult tasks. But promising work that is showing good results so far. The radiography example with those heat maps showing narrowing in the medial tibiofemoral space in osteoarthritis, or narrowing of the joint here, showing what the computer is looking at. Wisconsin's also been real active in this, and so they have their neural network, deep network diagram showing, and this is for detecting cartilage lesions. Again, all these ROC curves are very high. They could use that cartilage detection and build that into like a 3D segmentation model that allows you to do these types of 3D modeling. I can give this out. There's several articles that are good because as we get into this area, there's some good work coming out about how to think about and how to analyze these papers. And these are 3 papers that I would recommend that are fairly recent in AJR or radiology. So we talk a lot about diagnosis and that end, and it's kind of sexy to talk about that, but the imaging value chain, if you will, that's Greg Zaharchuk put this slide together for me, or lent me the slide. We talk about AI and image interpretation, but it's cool and it's sexy, but actually a lot of the value might actually come here, where we have early things like protocoling, hanging protocols, image reconstruction, and things like that. So this whole list, which I won't go through, it's all stuff that isn't really necessarily image interpretation, but it's things that actually could be better, improve quality, decrease dose. Who wouldn't want a better PACS hanging protocol, for example? That would be awesome. So that's where a lot of the wins are going to come in. Greg's working on some cool work with denoising images and showing better image contrast in things. He's got a company that shows that you can do like lumbar spine MRI with a certain standard acquisition and then shorten that by about half. And I don't know if you can see, but there's much less image noise in this image. And I'll tell you, if we could get more patients through the scanners, right, that's what the administrators are going to start to pay for, right? I don't know if anybody's going to buy that scoliosis algorithm or bone tumor algorithm, but they'll pay for patient throughput. Just quickly, a little bit more work from Stanford, Akshay Chaudhary, about he's actually predicting higher resolution images from low resolution images. Complicated way of thinking about things, but you can probably use modeling with AI to predict what images ought to look like. It remains to be seen how useful that will be. So I think we're still sort of third base. We're not quite at home yet, but how do we get there? And I'm not sure I have all the answers, but I just want to highlight one quick experiment that we're doing. Is like, so we have all this bone tumor data, right? And now we're like, does it actually work? Do people, how does it perform compared to experts? And so we did a little experiment where we took 20 lesions and presented to 30 pretty expert bone radiologists. We had them rank the diagnosis, aggressiveness, and we ran it through our machine. And here's the lesions. It'd be fun to dwell on this and have you all sort of take the test here, but we don't have time. Buried lesions, and notice in this there's a bunch of different backgrounds. So one of the challenges about bone is that it's not all just in the same image background, so it makes it harder for the computer to do it if you're doing image analysis. I've titled this busy, unreadable, and confusing because it's too much, but I just want to point out all the ones that are concordant examples were a match. The discordant ones were the computer and the humans disagreed. So here's the net summary. Humans recorded the true diagnosis as their top choice in 18 out of 20. They did really well, 90%. The computer got 75%. And humans and machine agreed on the top choice in 14 out of 20, or 70%. So the way I look at this, it's early, but experts are experts for a reason. And so if you're experienced, you can be pretty good. The win for this is going to be taking non-experts and people that are not good at it and saying, can the computer help you get more to the expert level? That remains to be seen, but that's the sort of thing we need to test. So we're inching a little bit more towards home, but we're nowhere near there. Last couple things. So this the interfaces. So here's our interface, and actually you can go to this website and you can play with the Bones Bayes machine. You can put in all the features. You're looking at an image, you put in the features, say, what would this be? And it might give you, it'll give you a differential diagnosis, make you sign a waiver. This is another interface that one of our fellows created a couple of years ago, where it's like, provide something cool and potentially useful. So this, what you do is you click on a bone, and then you click on images that look like your image, put in the age and the location, and you submit, and it basically computes for a minute, and then it spits out the differential. So we want to have really good user interfaces for these things that people actually want to use. Or maybe it's just all completely automatic. You just click on the lesion and it says, you know what, this looks like an enchondroma. So where are we now? So are we going to go back into the winter here? I don't think so. I think here are the options, right? We're going to continue this super hype of the world is so great because of all the AI. Nah, I think it's unlikely. I think the hype will fade. We'll get some useful applications. Right? We're not going to go off a cliff and go into a third winter in AI research. So just some summary points on the deep learning stuff. It's really powerful. It's broad. There's a low barrier of entry, right? I mentioned you don't have to know how to write code to do this. So that's good, and maybe it's also bad. Data sets are becoming available very early. The disadvantages are there's a low barrier to entry, so everybody's doing it. Lots of action out there, and some of it's not that good. The resolution issue I mentioned, the huge data sets. So this is an important point, I think. If you, let's say you have 100,000 images and you have an algorithm that gets 75% accuracy, and you're like, oh, let's figure out what those 25% were that were wrong. And I say, Thomas, do you have time to look at 25,000 images to troubleshoot or Rami or anybody? Right? It's like, no, you don't. So there's another black box there that we're dealing with. And there's just no proof yet of improved outcomes. Another cool quote that's sort of prescient here is from Lodwick. And he said in 1966, I think, effectively accomplished computer-aided programs will provide all radiologists with the opportunity of employing the unique approach of a specialist that may have spent their lifetime studying a new segment of disease. And so if we can do that, but this is, what is it, 53 years later? We haven't gotten there yet, so there's a lot to be done. There's a lot of cool technology, but it's, we don't want to be many years ahead and have that same quote be true. So finally, I'm thanking my predecessors and Gabrielle Bergman for allowing me to become a bone radiologist, even though I was like a body guy, and Gary, and then all the current people that I'm working with. So, and thank you all so much for your attention.